Okay, we are live, or at least we're being recorded now. So, welcome friends to how to differentiate. So, the purpose of this is for people who are, for example, learning about Olympiad inequalities or whatever, and they run into this thing called Jensen or tangent line trick or whatever, and it requires them to take a derivative. And if you normally the American math system hammers derivatives into you really early on, but some of you are very young and you haven't taken calculus yet, so this is going to be like 10-minute crash course on what this derivative thing means and how to compute it, and we're going to not do any of the details properly. It's going to be great. Okay, so first of all, quote-unquote definition. What is this derivative thing? So basically the idea is, suppose I have a function. For example, I'll take as my dummy example f of x equals x squared. Why not? And I can take a random point here, let's say like this 3, 9. So that's a function, and here's a point on it. And the idea, there's a couple of ways you can think about it. I think the most pictorial way is that at this point, I want to be able to approximate this function by a straight line, i.e. to draw a tangent line to the curve at that function. So there's this green line, which is like tangent to f of x equals x squared at 3, 9. Another way you can think about this is that you're approximating f by a linear function near 3, 9. What that means is that if I have a little epsilon, then I want f of 3 plus epsilon to be approximately equal to like 9 plus like a slope times epsilon. So, yeah, that's what the derivative is trying to do. And what we do is we give this thing a name. This slope, I have a line, it passes through a point, so all I need to do is tell you the slope. This slope is called the derivative of f at 3. And we write this as f prime of 3. And if you want to be formal about what this approximation sign means, since you guys have a good understanding of everything other than calculus, I will tell you actually it just means O of epsilon squared. So that's what the goal is. So I want to be able to say what is the slope of the tangent line at this point. And whatever number it is called f prime of 3, i.e. the derivative of f at 3. Okay, so that's fine, but then it's like, okay, well, how do I actually compute this number? And I'll do it manually for f of x equals x squared because it's easy enough that you can actually do it by hand. If I want, you have 3 plus epsilon squared. If you look at the definition, it will actually tell you explicitly what it is. You compute this is 9 plus 6 epsilon plus epsilon squared. So if I want to approximate it by a linear function, it's this 6 here. And more generally, if I do this with n instead of 2, by the binomial theorem, you'll have a 3 to the n, and then like an 3 times, n choose 1 times epsilon to the n minus 1, or not n minus 1, sorry. That. 3 to the n minus 1 times eps times n choose 1 plus eps times epsilon, and then plus lower order terms. So this would, if I had replaced x squared with x to the n, the slope would now be 3 to the n minus 1 times n. Here the slope is just the special case, like 3 times 2. Okay, for people watching in Discord, okay with me so far? Does it suffice not to calculate anything with epsilon squared in it? Yes. Yeah, but you can take as a definition either O of epsilon squared here, or little o of epsilon is also okay. Yeah, so basically I just want to approximate it by a linear function. That's what it's saying. Usually the definition given is little o of epsilon, but it turns out by some various calculus theorems that's basically equivalent to big O of epsilon squared. Okay, so we now know how to calculate all the slopes, and what you can see is for the x squared case, the slope is just always like twice the input. So if I'm at 3, 9, the slope is 6. And if I was at, say, 5, 25, the slope would be 10. And so at this point, we're going to do something which confuses the heck out of every American high school student, which is that I'm going to write f prime of x equals to x for f of x equals x squared. And this is like not very... This is a convention that you just can't get rid of now because it's everywhere. But I don't really like this convention because it's like you had... It feels like a bit of an abusive type to me, because now the derivative you really want to think of as a slope at every point, but now the type of object is like a function again. But okay, well here we are. This is how it's written. So I showed you for 3, since in general for x it would be 2x, we write f prime of x equals 2x, and now I have a new type of function, which is typically written f prime. You'll also see this written as df over dx in some places, which is fine. You know, f prime, they mean the same thing. So this is the definition. It's like for at every point x, you can approximate f of x near that point by a linear function if your function is well enough behaved, and the slope of that thing is denoted f prime of x. Okay, yeah, Discord observers, any questions up to here? And can whoever keeps posting integration exercises please stop? Okay, great. So that's great, and basically this is what it means when you see someone says the derivative of x squared is 2x, this is what they mean. It means at every point you can approximate it by 2x there. So this is fine, and this leaves the question of like, okay, great, I know what this f prime like is supposed to interpret, how do I actually compute it? And it basically turns out that there is this big recipe that you can follow that for any function that's that you would ever encounter in practice, you can actually just differentiate it. So let me explain. So first of all, what I'm basically going to do is give you a bunch of theorems, and together these theorems will let you deal with any function that you'll encounter in real life. So first of all, if I have x to the n, you already kind of saw by the binomial theorem, this ends up being n to the x, n times x to the n minus 1. Okay, now I'm going to give you a couple more black boxes. E to the x goes to itself. Sine x happens to be cosine x, and cosine x happens to be minus sine x. Also, this x to the n actually doesn't work just for integers. This will work for any real numbers. So if you have square root x, you could also compute the derivative using this. So okay, so these are the ones that I'm going to take as the base. Like, if you have these, well, these are the ones that actually require a bit of work to derive from first principles. Next, differentiation is obviously linear because, you know, if I'm approximating by linear functions, they just add with each other. So if I take a constant and multiply it, like 2x squared will have derivative 4x, and 10x squared will have derivative 20x. Also, like x squared plus x cubed will have derivative 2x plus 3x squared. So it's linear in this way. Secondly, it's what about products? So if I have f times g, how can I differentiate it? So this thing is in American education called the product rule. And the way you remember it is, again, you're trying to approximate by linear functions, right? So I have an f of x, g of x. This is like the product. And I want to like change x by an epsilon. Well, you know, this is like this is roughly epsilon times g prime of x. This guy is like epsilon times f prime of x. I put the prime in the wrong place. And then here's some stuff that's like O of epsilon squared, so we don't care about it. And so when I do that, this suggests what the answer should be, and I will not bother to rigorously prove this because we're in like the American system here. So this is f prime times g plus g prime times f. Yeah, and you can use this, for example, as sort of another way to verify the product rule, because the derivative of x is obviously 1. Sorry, not product rule. The base example with x to the r. Like if you wanted to do x squared, you could have done it times x. But binomial theorem, I think, is much more conceptual. Yeah. I think I forgot one base example I wanted. You might run into logs in Olympiads as well. If you see a natural log, its derivative is 1 over x. So these are sort of the 5 base ones that you'll encounter in math contests. So the last one I want to do is the one that's the only one that I won't give an explanation for why it's true. This is like the chain rule, which is that if I have a composition of functions, for example, f of g of x, the derivative of this happens to be equal to, okay, I hope I remember what it is. It's like f prime of g of x times g prime of x. And because I want this video to not be very long, I will basically take this as a black box. And basically, using this stuff on the board, now if I give you an arbitrarily horrible function, you should be able to just like compute its derivative. Let me give an example that will sort of just use everything. Suppose I have this completely random garbage function like x log x plus 3 1 over that all squared. Like, this is a function. You probably won't run into a function this bad unless you're doing inequalities, but let's just say this appeared. And you want to compute its derivative. Well, basically, you just follow the recipe and it'll just work. So first what happens is it's a composition of 1 over x squared and this thing inside. So what's the thing inside? Well, what's the derivative of 1 over x squared? By this base rule, it's like minus 2 times thing to the minus 3. So the first thing I do is I write minus 2 times like x log x. I don't change this inside for now to the minus 3. And then I have to differentiate x log x, whatever the derivative of this thing is. Okay, and then to differentiate that, well, first now differentiation is linear, so I can split this into 2 parts. This part is a constant, so its derivative is just 0, it dies. This part is a product, so I can look up on my table and say, what do I do when I see a product? I use this so-called product rule. And so the product rule on x log x gives you x prime times log x plus x times log x prime. Okay, and now you look at the table and see what are these. Well, if you were paying attention, you should know that x prime is just 1, so this is just 1. And log x is one of the ones I gave you in the table, it's just 1 over x. Okay, so now this is just the answer. It's like minus 2 times x log x plus 3 to the minus 3, and then times whatever happened inside, which happens to be just log x plus 1. I hope I did my differentiation correctly. It would be very typical of me to mess up. But yeah, so basically, given an arbitrary function, this is the recipe that you will be taught in American calculus to actually compute the derivative. Yeah, and I think that's literally it. This concludes how to take a derivative 101. Yeah. Are there any questions? Is integration useful in Olympiad? Much less so. It's typically, I think the most common use case is if you have like a sum you want to approximate. Like suppose you have like some I don't know, 1 over n squared, which, if you want to approximate that with, like, bare hands, the easiest way is to bound it from above by an integral. How do I use this for convexity and concavity? Okay, fine. I'll tell you. Okay, so the definition of convex. The definition of convex is that if you differentiate it twice, it's non-negative over that interval. So for example, x squared is convex everywhere because its second derivative, if I differentiate it twice, I get x squared to 2x to 2. And that 2 is not non-negative everywhere, so f is convex everywhere. Also, f is increasing exactly where f prime is non-negative. So if you want to check if your function is increasing or decreasing, you take the derivative once and then see where it's positive. If you want to check whether your function is convex, you take the derivative twice and see where it's not negative. And if you draw some pictures, you will see why these are sort of the correct things to take. Is there a geometric definition for convexity and concavity? Yes. It says that it's basically Jensen's inequality, actually. It says if I have a function and I take any point like this point will lie above that point. Yeah, that's what convex means. It's like if I take a weighted combination of 2 points, it lies above the actual curve. Is the use of increasing function used a lot? Yeah, pretty often. Like, one very common thing is, like, for example, suppose you just have some dumb inequality that you know is true for all large enough things, but is annoying to prove rigorously. Like, say you need, like, 2 to the n is greater than 3n for large enough n. A way you can prove this manually during Olympiads without using your brain is you say, like, okay, well, past a certain point, 2 to the x minus 3x has positive derivative. So now it is just positive. What is the derivative of 2 to the x? So the way you can get it from this table I gave you is to write it as a composition. So what I'll do is I will say, let me do it up here. 2 to the x is equal to, like, e to the log 2 times x. And so now you can use the chain rule. So e to the e stays the same, and then you get just the derivative of this guy, which is log 2. So it's 2 to the x times log 2. Yeah. So really, these 5 base ones and these 3 general rules for math contest purposes are basically all you're ever going to need, I think. Like, yeah. The one that confused, when I was a little kid, the one I really could not figure out was x to the x. I was like, how am I supposed to differentiate that? And what you do is you write it as, like, e to the x log x, and then you can do it. That's just a random thing in passing. Yeah, I didn't cover differentiation both sides of an equation because I wanted to keep this, like, pretty minimal. Like, you're not going to need to differentiate both sides for the functions you encounter in math contests. what is an inflection point? An inflection point is when f double prime is 0, so it's when a function switches from convex to concave. Yeah. So like for example, x cubed has an inflection point at the origin because here it's concave and here it's convex. This is x cubed. So this is the place where it flips. And yeah, we call that an inflection point. That's just a name. Yeah, depending on who you ask, I think in most definitions they do require that it actually changes sign, not just that the double derivative is 0. So it basically you need to switch from convex to concave or vice versa. Okay, any other questions? Okay. In that case, thanks all for attending Calculus 101. If you're curious, in AP Calculus BC, this will be about half a semester working on just this. The other half is integration. So congratulations. We will now adjourn.